Into this tutorial, I'll show you how to model thermal buckling. It is very similar to buckling due to any mechanical loading, but here the buckling will be primarily due to the thermal loading, due to application of temperature. Here I am following this paper. This is a paper on composite structures. I'll follow this paper, this example, the experiment that's been carried out in this paper. Here, as you can see, there are two circular plates, one circular plates, and there is an annular plate, and this of two different materials, and they are subjected to some uniform temperature loading. Since the two different materials, one is epoxy composite, another is the circumference is the titanium. Since there is a huge difference in the coefficient of thermal expansion, so when they are subjected to the same temperature, because of the difference in the coefficient of thermal expansion, the inner fiber reinforced composite will expand different than the outer ring, and this will since the CTE of the epoxy is larger than the titanium, then it will expand more and expand more, and it will experience some compression. And of course, the thickness of these two plates are different. For thickness for this outer ring is around 10 mm, and the inner one is around 0.09 mm. And because of this compressive force, and this inner plate will buckle. That is the idea of this experiment. Okay, but during Abaqus simulation, I'll not going to model each and every detail. Not going to model this gap. There is some small gap between the inner plate and outer annular plate, so I'm not going to model that. That is that will be some task for you. Okay, as I was telling that I was just telling that buckling, thermal buckling is very similar to mechanical buckling due to mechanical loading. So let me go to Abaqus first. This is my, I already created a few models for you so that I can make this video faster. Okay, I'll go quickly show you the steps. First of all, I will be carrying out a the eigenvalue analysis. As you know that buckling problem in general, the linear buckling analysis, it is basically eigenvalue problem. We are solving eigenvalue problems. So I'll show you in Abaqus how we can do that, how we can obtain a different buckling modes for this problem. And here I will also discuss about the different boundary conditions I have used. All right, so this is the first geometry I have created using as a shell, and the radius of this geometry is about 30 mm, and I have created this partition to assign different material for different region. And then I have created these shades. This is the epoxy glass, this inner region is for epoxy glass composite, the outer region is for corresponds to the titanium. Okay, and I have created some other necessary shades like to visually useful for applying boundary conditions. Then I have assigned the property. I have created the material property, and these material parameters are taken from that paper I have shown you earlier, and the link for this paper will be provided to you in the readme file. And these are the modulus of elasticity and the thermal related parameters. And then I have applied different material for different regions, as you can see it here. After that, what I have done is I need to bring the part to assembly, and need to create a step. Here I have created this step. This is called I will show you. This is there. Okay, I'll not replace, but I'll like to show you what kind of analysis step we are using. This is a linear perturbation analysis, and this is buckle is specifically developed for buckling analysis. And of course you cannot use this is a very linear elastic analysis. Buckling here is a linear elastic analysis. And all right, let me show you the boundary conditions. Okay, so for boundary conditions I have restrained the all right, I have at the outer periphery of the problem. I have restrained the outer periphery. Okay, I have created a second a new coordinate system to allow. All right, I do not need this. Okay. Here I have restrained all the displacement degree of freedom at the outer periphery except the lateral one. Now our model has been prepared primarily for using rectangular Cartesian coordinate system, but we need something in the normal direction. So here I have created a new datum coordinate system considering a new cylindrical coordinate system. Okay, I can quickly show you how you can do that. Let me create one. Let me show you how we can create such boundary condition using a new coordinate system. Here I have select a new boundary condition. I like to create one, say same for the outer region. Okay, now continue. Now by default, as you can see, it is used as a global coordinate system. Now here you will go with this and datum coordinate system, and from here I have created already a new one. Okay, so let me show you how you can create a new one, right? So go to tools and datum and COAS, and you can use 3 points and a cylindrical and continue. So the center point, of course, the 0 0 0. And it's ready. Okay, so you can check this newly created coordinate system here. See, this is the new one. Okay, which also overlaps with the previous one. Okay, so I will just suppress it. Okay, and no longer use it. So like this, I have created. I have used a this cylindrical coordinate system instead of the global coordinate system in defining this boundary condition, because I want to only restrain and I want to allow okay, here I restrain everything, but in the step 1 when we are applying the load, I want to allow the radial direction, because in cylindrical coordinate system we have r, theta, z direction, r, theta, z directions, right? So r, theta is the first direction, r is the first direction, the radial direction. So I want to allow the movement in the r direction, and the arrow you are seeing here, this is due to I have applied a load, right? We need to, these are the boundary condition, this one boundary condition I have shown you. Now we need to apply some load, right? This is the load I have applied. This is a shell edge load. I want to apply a normal traction, sort of a compression, because we want to simulate what is the amount of normal traction onto this system, so that it can it can buckle, right? And I want to study the buckling modes under such a loading condition, right? So this is the magnitude is 1. This does not matter, it's just a reference value, and your eigenvalues will be some multiple of this value what I have given here, right? Now let me go to the mesh module. Okay, I will use a simple 4 noded let me show you what type of element I have used. So to do the meshing, you can check any other Abaqus tutorial. So I will show you what kind of mesh I have used here. So I will go array mesh and you can see the details here. So I have used S4T, so 4 noded shell elements with thermal temperature, T for temperature degree of freedom. But okay, so this is for eigenvalue analysis, a simple eigenvalue analysis. So temperature degree of freedom is no use here, but just I have kept it for generalization, right? So after this model is ready, and yeah, I have shown you the loading, the mesh, and so you need to create a job. I'll just delete this my old jobs. Okay, this is no longer valid, right? So I've created this model M2 eigen for model to for this model, right? And I have submitted it. Okay, I will submit the job. You can edit. I can show you. Okay. I submit the jobs and it's done. Now I show you the results first. Okay, right. See, okay, this direction looks good. This is the first mode and this is the first mode shape. I'll plot the displacement. Okay, maximum displacement at the center because it is compressing. And this is the eigenvalue. It shows that about 2.5 you can say MPa, because I have applied as I told you earlier that I have applied as a reference surface extraction on the outer periphery of the shell, and we need some 2.5 times of that that forces to have this first mode of buckling. And similarly for second mode, we need, this is the second mode of buckling, it will need a 4.5 to 46 MPa. And this is third mode, is the same as the first mode but symmetrically opposite. And this is the fourth mode. As you can see, you need more larger larger forces, applied forces to obtain this mode. Okay, so why these eigenvalues and modes are important? Okay, this from this we can understand the basic buckling modes of the problem, how it may buckle under different loading conditions. Because when we apply a real when we subject the structure to any realistic loading condition, if it is purely predominantly a compressive one, and it may buckle, and that may consist of different the actual deformed shape may be consist of the multiple buckling mode of the structure, right? And our another during this creating this job, I have also done another thing that all the I've seen we are seeing this result on Abaqus ODB, the output database, but we can also store the data in a different database so that we can use it later in the simulation. I will show you how we need to we cannot do that using geographical user interface, but we can edit the input file, or we can edit this keyword here, like to write to a different file .fil actually. So I have added these few lines in the modal output. This is the comment note print, where I like to print the displacement and star model file. These few lines will write the Abaqus the model informations like the eigenvectors or the deformed shape of the structure in different modes to to another file, and which can be later called in a which can be used to introduce some imperfection in our structure, right? So this imperfection is actually important to model. Otherwise, if you think since we are doing a numerical study and this is in a very ideal condition, so there is no inherent imperfection in our model. If you start compressing this shell, and you may find that it is keep on compressing it because we are considering a linear elastic material model, and there is no buckling, right. So but if you think of experiments, there is always some imperfection involved by in nature actually. So but in numerical study we need to introduce some imperfection, and maybe a very small magnitude, but we need to do that. Now I will straight away go to the our main problem, that is the thermal buckling. So the difference is I take the same model, make a copy like something like this, create a copy of the model, and I have renamed it to model 4 thermo, and the changes are primarily here. Instead of the buckling procedure, here I have a coupled let me show you what are the different options are there. I have used this one, coupled temperature displacement. So this procedure is for the coupled temperature displacement. Like we can, here I will be considering the temperature degree of freedom along with the mechanical, that is the displacement degree of freedom. Let me show you the details here. So here we can use a steady state and transient in terms of the temperature. Okay, I will consider a steady state because I am going to apply a uniform temperature all over the domain, and you can try but for different problem we can use a transient one, where we apply a temperature or we apply some initial condition on the temperature, and temperature will evolve with time. And for buckling analysis, since we are going to do a buckling analysis, this nonlinear geometry, this is a consideration of the finite deformation in our calculation is important, so we will make it on. And this is the analysis increments. So as you can see the numbers, so it is the initial one and the minimum value and the maximum one. And okay, this is the change. I am not going to change any changes in, okay, make any changes, and you can modify any output you want to add here. Okay, this is a field output, and history output I have added a few, but the most important here is the what is the going on at the center. So I am trying to record the displacement values and the temperature, nodal temperature at the center of this specimen. Okay, right, and we have the same mesh, and here in the loading condition is slightly different. It is again the same boundary condition as before, but I have restrained the horizontal displacement, we have the radial displacement. I have basically completely fixed the outer periphery of the structure of the specimen, and applied a uniform temperature of magnitude 5 degrees Celsius, you can say, over the entire domain. And in the amplitude I have used a amplitude 1. It is basically, let me show you what this amplitude is like. Alright, amplitude, yes, amplitude is here. So this amplitude is about at t equal to 0 the amplitude is 0, and time equal to 1 the amplitude is 1, like it is a ramp function. So it is smoothly it's a linear function, as you can understand, right. The temperature will be linearly increasing over the time. Okay, so again I have as I have told you earlier that I am recording the mode shape in a different file, so that I can use it for modeling the imperfection in our actual structure when I am doing a buckling analysis under temperature loading. So how I have to, okay, there in the through graphical user interface you cannot do that, so you need to go to again edit keyword, or you can write the input file .inp file and you can modify add a few lines there. So here are the following lines which I have added. So let me show you here. All right, here after boundary condition I have added this line. So I have added this keyword star imperfection is the keyword for an Abaqus to add the imperfection here in the model. The imperfection in terms of that you have a original mesh, and you are basically saying that okay, the original geometry is not what is created by the mesh or created by the geometry, of the problem what I have developed in ABACAT, but I want to add some nodal deformation, which is the initial condition to the model, right. So this is the imperfection starting point, and the file is m2 eigen. M2 eigen is the file name of the model I have created previously, and here I am going to take the values from the step 1 of the simulation, because there are two steps. Step 0 is the initial step, and step 1 is for the buckling analysis. And here I am going to take the mode 1, this one mode 1, and I am introducing a scale factor, very small value, that the imperfection, because the mode shapes are normalized to a value of 1. Okay, maximum displacement for any mode shape is 1, because it's a eigenvector, it's a the values, I mean it is the relative numbers what matters, right. So in Abaqus it is normalized, so maximum value is 1. So I am saying that okay, I want to scale it down to say 1 into 10 to the minus 4, like 1 in 10,000, right. So I want to take a very small value of imperfection. I want to consider very small value of imperfection here. Okay, after this is introduce this, because introducing imperfection is very important, otherwise you might not see, as you were telling you earlier, that you might not see that there is there is no buckling, right. Now again you will create a new job, and I have already created the job and submitted, and the job is completed, and I am going to directly show you the results. Okay, this is not the result for static, but this is for the buckling analysis. Now I am going to show you. Okay, all right, let me show you. It does not look like you have a very large buckle deformation, but it has something. All right, so this is the initial shape. You cannot see it is a almost perfectly horizontal geometry. See, there is no, okay, but if you go step by step, see, there are lots of central deformation, and if I plot you the deformation contour, the maximum displacement, and we were interested in the displacement in the 3 direction, right, this third direction. See, so at the outer periphery the displacement is 0, because this is the boundary condition, but the inner periphery, I will have to show you how the temperature look like. Temperature is uniform here, as you can see, it is 1.253 and continuously increasing with a load step, and see the displacement is continuously increasing at the center, and I like to show you, see, continuously increasing. Now I like to show you the like to plot what is the history of the displacement at the center. So for that I have recorded a few at the center, and the vertical displacement at the center, and save as, and we combine it, swap variables, no, not swap variables. Okay, so on the x-axis I have kept the temperature, and the y-axis the displacement. So initially with increase in temperature up to say less than 1 degree, so there is no vertical displacement. Okay, but about temperature 1 degree, certainly there is a very huge increase in the temperature. So as from this plot we can say that okay, there is buckling, because we are continuously increasing the temperature of the specimens, and because of the difference in the coefficient of thermal expansion of the inner region, it is trying to expand, while the outer one is not expanding so much, and because of the difference in this expansion, the outer ring, which is a very heavy one of thickness 10 mm, will give a compression effect on the inner plate, and because of that buckling, it is the inner plate is buckled, right. Of course the displacement value is not in so huge, but yeah, we need to think that it's a very different kind of problem. It's a thermal buckling, and we can see that of course the temperature dependence of this displacement is a non-linear one, right. So like this we can model the thermal buckling. Here in this problem I have considered a continuously or monotonically increased temperature loading under a steady state condition, but one can do a similar study for transient loading, transient temperature loading. And because of thermal shock, like when you are suddenly applying temperature to a certain region of the structure, and it will create a shock, and because of this transient of the problem, the thermal buckling will be very different. And of course, and there is another thing, interesting thing, that for this problem I have used to imperfection based on the first buckling mode of the structure, and that's maybe that's why you are seeing this kind of buckling mode. Like at the center it is the maximum displacement, and at the single point or the central or the symmetric one. And you can try with a different buckling mode, imperfection based on different buckling mode, like mode 2 instead of mode 1. You can mode 2 or mode 3 or mode 4 to see how the initial imperfection affects the final buckle shape of the structure. Okay, that's all for this tutorial. Thank you so much.